Okay, 12:40. We're allowed to get started. Welcome to lecture 4 for 127-227A. Thank you everyone for coming here on this hot day. I will try to make the class as entertaining as possible to make up for the fact that it's basically boiling outside. We're going to pick up where we left off last time. And I'm going to have a demo in the middle, so that's why the screen is still down. So if I raise the board, you're not going to be able to see it. But that's just going to happen for the first half of the class, because I am not confident enough about raising and lowering the screen again to get this to work. But we're going to do a little bit of a demo in the middle, and then we'll come back to the board for all of the math part of the class. So last time we left off talking about the spectral theorem for symmetric matrices. And just as a reminder, what is this spectral theorem? Well, it says that if A is a symmetric matrix, you can express A as some U lambda U transpose, where U is orthonormal and lambda is diagonal. Just as a point of reference, by the way, a lot of different textbooks use the word unitary instead of orthonormal. Unitary matrices and orthonormal matrices are the same thing. I just like the word orthonormal more because the word itself describes what it means, right? It means that the columns are orthogonal and they're normalized. And unitary is kind of like, well, there's some unitariness, but it doesn't capture the orthogonality of the columns. So in this class, we're going to preferentially use orthonormal, but know that unitary means the same thing. This is just for you and your external lives. Okay, so one of the nice things about this kind of decomposition, right, is that it allows us to read off lots of things about the, let's say, range space or null space of this matrix A. So for example, let's say that A was of the following form. So if I had A is equal to U times lambda 1, lambda 2, all the way up to lambda r, and all of these are 0. So I organize my eigenvalues in increasing order, right, of absolute values. So if I had, let's say, or lambda 1 greater than or equal to lambda 2 greater than or equal to lambda r greater than or equal to lambda r plus 1, and all of these are 0. Okay? If I had, let's say this is the matrix that's given to me, right? Let's not even worry, in fact, about the increasing order. Let's just say that we organize all of the non-zero eigenvalues and followed by the 0 eigenvalues. If we had this, and I asked you, well, what's the null space of A? Can you give me a basis for the null space of the matrix A? How could you do this? Someone else who hasn't spoken before. Someone who hasn't spoken before. Yeah. Yeah, it's the last n minus r columns of U, right? So if everything here in this block is all zeros, whatever hits this is going to be completely sent to 0 always, right? So if I expand out this U, U1, U2, and then I have UR, and then UR plus 1, all the way up to, let's say, UN, all of these guys, similarly here, the last n minus r rows, they're all going to hit basically these rows that are all zeros and these columns that are all zeros, right? And so you can easily read off what the null space of the matrix is, right? Similarly, if you had to read off the range space of this matrix, given this nice decomposition, what would the range space be, or the column space? Kind of the other part, right? The stuff that isn't going to 0, right? So all of this This will correspond to the range. This will correspond to the null space. Turns out that this kind of decomposition is something that is incredibly useful for us, and that's how we're today going to build up towards understanding the singular value decomposition, which is what will allow us to do this not just for a special symmetric matrix, but for any general matrix, right? So you'll be able to write it out in a way that immediately you can read off what the null space and what the column space are for the matrix, okay? So before we get to that, I want to build on the symmetric matrices part and do one quick optimization problem that turns out to be quite useful, not only for us, but in general. And this is what is called the variational characterization of eigenvalues of a symmetric matrix. And what we're going to see is that, consider this quantity. So I'm going to call this, what do I want to call it? Let's just call it R, which is equal to X transpose AX divided by X transpose X. And A is a symmetric matrix. So this on top is what we call the quadratic form. And this is something that we will come back to when we start talking about QPs, quadratic programs in particular. But this is basically the vector equivalent of a quadratic, right? When you have, for example, a quadratic polynomial in scalars, you have ax squared plus bx plus c, something like this, right? But now when my variables are vectors, the quadratic form corresponding to a particular matrix A is the following. And of course, there could be a linear term and a constant term as well. But here we're just thinking about the quadratic term. That is what this is. And we're dividing it by this quantity. What is this quantity? Is this a vector or a scalar? It's a scalar. This is just the norm, right? This quantity is called the Rayleigh coefficient. And the nice thing is that we can actually use this to characterize the max and minimum eigenvalues of this matrix. So lambda min, the smallest eigenvalue of A, is upper bounded by this quantity for all x. And this is always smaller than the largest eigenvalue. A more useful thing, or a useful way of writing this, might be the following. Lambda max of A is the max over all norm 1 vectors of this quantity. Okay? And similarly, you can write the lambda min expression. So take a minute and see how you might be able to actually prove something like this using the spectral theorem that we just talked about. So here, again, what are we saying? We're saying we're given a particular matrix, and we want to be able to connect the interaction of this matrix with a particular vector. So we're thinking of A times X, you know, here we're thinking about it in the quadratic form sense, and we're looking over unit vectors. And we want to see what is this quantity. And turns out that this is deeply related to the maximum and minimum eigenvalues of that particular matrix. And why this is useful is going to come up in the second half of the lecture. So this is an optimization problem that just seems like kind of a game for now, but it's going to be useful very, very soon. So take a pass at it, talk to your neighbors, you know. All of you hiked here in the heat to be here in person, so, you know, talk to each other. Question?
Is there any way to let people react
There is not a way to lift that screen right now because I need that screen for a demo later on, and the lowering and raising the screen is tricky. So for the second half of the class, it will be raised, but right now we don't have a way of doing that. Yeah? Can lambda min be negative here? Lambda min can be negative in general. However, what you can also show is that for a symmetric matrix, all of your eigenvalues are going to be non-negative. Lambda min could be 0. But it cannot be negative. Okay, let's work on this together. It's a bit tricky, right? So let's use the spectral theorem that we know. So let's say that I know that I can write out, oh dear. Let's say I know that I can write A as U transpose lambda U, right? I know that I can write this particular formulation. I want to say something about this quantity, right? So can I write X transpose AX? Can I expand this out and can I connect these things? I want to be able to pull out eigenvalues, right? This form allows me to pull out eigenvalues, kind of, right? It makes them explicit along the diagonal. So I want to try and connect these things up. So what am I going to do? Substitute, right? There's basically one thing to do here, not that much variation. So I'm going to write this as X transpose U transpose, sorry, this is a matrix, A U times X, okay? Except I don't want to have an A here, right? What do I want to have? Lambda, yeah. Now, what do I have here? Can I replace this somehow? What U is now an orthonormal matrix. X is a unit vector. So what do we know about orthonormal matrices multiplying unit vectors? Yeah, give me a minute. Let me finish this and then I can ask. But yeah. Orthonormal matrices, the nice thing is that they preserve norm, right? They won't change the norm. So if I define Ux to be equal to some vector y, y is also a unit vector, right? So I can write this, and this guy here is just going to be y transpose lambda times y. What's your question?
Why are we able to write A as U transpose?
Because A is symmetric, and we're using the spectral theorem, which we just talked about.
Okay, before you wrote it as U lambda U transpose?
Oh, U lambda U transpose. It doesn't matter, right? Because these are orthonormal. It doesn't matter how you write them. You can generally it's simply equivalent. It's completely equivalent to writing it this. It's a different U. This decomposition is not unique, right? So it doesn't matter where you put the transpose at all. Yeah. But here you can just define a different U, like define U1 to be equal to U transpose, and you get either representation, right?
Does the proof change at all, though, if you use U lambda U transpose, though?
It does not change at all. If people want, how many people want me to go through this proof using U lambda U transpose instead of the way I have it right now? You want to do that? All that would change is you would write U transpose X equal to Y. Nothing would change, right? Y would still be unitary. U transpose is still a unit vector, is still orthonormal. Would make absolutely no difference to the proof. Does everyone see that? Okay, good. So let's stick to this way we have it right now. So can you write this out? I want to pull out the eigenvalues. Can you write this out in the way that pulls out the eigenvalues? What is this equal to? I can write this as lambda I yi squared, right? because this is just a diagonal matrix. So all this gives me is a version of y scaled by lambda I multiplied by yi transpose, that's just the dot product, which gives me this. Everyone see that? And now we're going to do the trick that we've been doing a couple of times in lecture already, right? So now I want to bound this quantity. I want to upper bound it and lower bound it, right? So how am I going to upper and lower bound this quantity? Is there something that I can say this is always smaller than in terms of these lambdas? Yeah. I can pull out the maximum eigenvalue, right? Every lambda I is less than lambda max. It's always less than the largest, right? So can I write this as less than or equal to lambda max yi square? Yeah? Yeah. But now, does this lambda max depend on I? Nope. So I can write it outside the sigma, not y max, sorry. This is lambda max. What's left inside? This is just lambda max times the norm of y squared, right? And now if we started off with x as a unit vector, let's say, if we're looking for this form, x is a unit vector, what does that tell us about y? Y is also a unit vector. So are we done? Does everyone see this? Any questions here? Yes? Okay. Everyone good till here? Lambda max gets pulled out. So now this thing I can just write as lambda max times the norm of x because of this, right? And I'm saying that if we assume that here we're looking at the maximization over all norm x equal to 1, so if norm x equal to 1, this implies that norm y equal to 1 because of our orthonormal relationship between the two. Yeah? This is true for any unit vector x. We've never used anything special about x here, right? Yeah?
Can you say anything about like this whole like scheme if x were to like not be unit vector?
The question is, can you say anything about this if x was not unit vector? You could. You would just normalize it to be a unit vector, and you could follow through the same exact proof. I recommend it as a homework exercise. Okay. So everyone see how this is now upper bounded by lambda max? Right? So therefore, now if we wanted to, we've said that the maximum value that this can achieve is lambda max. To prove that this max is actually equal to lambda max, what do I need to show? I need to find an x that actually achieves this, right? What is the x that I'm going to choose? What x achieves the max? What x are you going to choose? There's really one choice. Speak up. That eigenvector that corresponds to lambda max, right? So I know that there exists an x that can achieve this because by choose x equal to the eigenvector corresponding to lambda max. Yeah? Is everyone really quiet because it's really hot, or this is really confusing? I cannot tell the difference. Hot? Okay. Yes?
If
If Ivanhoe x is repeated, you could have multiple choices. That is correct. Absolutely. Yes?
Are we dividing by in the inequality lambda min is less than or equal to x transpose? Like, why are we dividing by the square of the norm when we want the vector norm to be 1?
Well, in this case, we're writing the vector norm as 1, and we're not dividing by anything. Here, we want to normalize. And here, we're not constraining this to be 1. So here, x transpose x is equal to the norm squared. This is just the definition. Like, this is just what x transpose x is equal to.
So what we're doing right here wasn't trying to prove that
This can be inferred from this by generalizing to a non-unit norm x. We've only proved it for unit norm x in this case. Okay? Yes?
Please re-explain, how does that inequality become an equality when x is equal to the eigenvector?
Okay, the question is, where does this x equal to eigenvector come from? So if I have x transpose ax, and x is an eigenvector, what does ax become? Lambda x, right? So then I have x transpose lambda max x, and now I have basically the lambda max comes out, so I have lambda max x transpose x. What is x transpose x? X transpose x is 1, right? Because we are choosing the normalized eigenvector. Yes? I'm going to take that question after class. Good question, but basically you have to, it's something that you want to choose to achieve this, but in the interest of moving on, basically you want to see that, you want to make this equal to lambda max, right? And so if I want a times x, if I want to pull out a lambda max, I'm going to have to choose a v which is equal to something that will pull out that lambda max. So if I choose this as v max, I'm going to get lambda max times v max out, right? Okay, I really have to move on. Ask me after class, okay? Unless you see something that I've done wrong or it's a typo. But ask your neighbor. Everyone who has a question, turn to your neighbor and ask them the question. Okay. So we've done a lot of work about symmetric matrices. And I told you that symmetric matrices pop up a lot, and they pop up frequently. And now we're going to talk about a case where a symmetric matrix is going to be particularly important. And this is principal component analysis. So for those of you who have taken 16b, this is going to be a bit of a review. But since we have a lot of people coming from different institutions who might not have had the chance to take 16b, we're going to kind of do this out. But we're going to do it in a slightly different way from the way 16b did it. So hopefully, even for those of you who have seen it before, there'll be something interesting to see. Okay? So principal component analysis is the idea of saying, given a bunch of data, I want to identify, as the name suggests, the principal components. What do I mean by the principal components? I mean those components that are most representative or most valuable, in a sense. Those components that capture the data. Fundamentally, if let's say I have some p-dimensional data, I want to be able to find an underlying q-dimensional structure where q is strictly less than p. And this comes up many, many, many times. Basically, a lot of the large data sets that you consider, any data set that you consider, for example, about the population, about any biological data, most machine learning data sets, for that matter, have vectors, have data points that are, 100, 1,000 dimensions long, for example. Visualizing something or trying to get an intuitive sense of a 1,000-dimensional data set is just really hard, right? You can't even plot it. And so the idea of principal components analysis is to say that can I project this data into some smaller dimension that allows me to kind of get a reasonable sense of what that data actually is. And for doing this, we often consider the following setup. So if I have some data, let's call them x1, x2, all the way up to xn. These are data points. Let's say they're p-dimensional. So each xi belongs to Rp. I'm going to define the data matrix X with this data along the rows. And different textbooks will do this in different ways, and there's different, the transposes can get tricky here. Don't worry about it. Just always do things out from first principles, and you will never get confused by a transpose. But there's people out there who like intimidating other people by using jargon and using fancy notation. We're going to try to avoid doing that. Always write things out from first principles. Here what we're going to do is we're going to write every one of these in the rows of the matrix. Right? So this is n. This is an n by p matrix. This is what we're going to call the data matrix. And you'll see why we choose to put this in the rows instead of the columns later. You can do, everything will work out if you choose to put it in the columns instead. It just makes a few steps of mathematics later down the line easier. That's why we're putting it into the rows. And so I have X transpose is this in the columns. Okay? And for this, I define C is equal to 1 over n times X transpose X. This matrix is a matrix that ends up being particularly valuable. When I write this as X transpose X, what's the first entry that I get? I get this times this. So what I'm going to get is basically norm squared along the diagonals. Sorry, I want XX transpose. Xn. And here I'm going to get so on and so forth. What is the nice thing about this matrix? This is symmetric, right? Okay. Did I do this right? Wait a second. Let me check that I've not made a typo. Okay, I'm not sure if I'm going to need this matrix or the transpose of this matrix, or X or the other matrix. So I'm going to define both of them, and then we'll use whichever one shows up. I'm going to call this, I'm going to also define matrix D to be equal to 1 over n X transpose X, which is going to give me another related matrix. So, but this is also going to be symmetric. XX transpose will give me this one. This will give me a matrix that's not quite exactly equal to this, but it's also symmetric. Sorry about that. I might need to use the matrix D later on. Yes, question?
Where's the 1 over n in this?
Oh, great point. Thank you. I should have a 1 over n here, too. Sorry. Yeah. I should have made that exact calculation out before lecture and not done it on the fly. Don't worry about the definition. It's not that important for us. The most important thing is that either of both of these matrices are symmetric. Okay? What I want to show you now is basically what I mean by when we're talking about principal components analysis. So what I want to do here is I want to find, I have all of these data points. I want to find let's say I wanted to find one principal component, the first principal component. I want to find some vector w such that if I project my data into this direction w, then I preserve most of my structure of my data. So for example, if I had just two-dimensional data, right? I was working only in R2. Can everyone see this here? I'm drawing in a bit of a corner, but can everyone see? Let's say I had data that was kind of like this. These were my data points. When you look at this data, yes, this data is two-dimensional, but is there a structure underlying it that you might want to pull out? Right? It feels like there's an underlying one-dimensional structure here, right? So when I say I want to find an underlying lower dimensional structure, I'm trying to look for something like this. And so here, if I could find this direction w, I could say, well, let me project onto that particular direction, and that would help me uncover the underlying structure. Okay? So in a larger setup, if I have a p-dimensional data set and I want to find an underlying q-dimensional structure, then I want to find vectors w1, w2, wq such that I can project into these directions and recover the underlying, structure. And how am I going to exactly mathematically characterize this? That is what we're going to be talking about in the lecture today. Okay. Oops, my screen went away. So let's try to understand this in the context of a concrete example. So how many people have heard of MNIST? Some people have heard of it. For those of you who haven't, it's the reason I wanted to introduce this in class today. MNIST is a commonly used data set in many machine learning applications. It's basically a standard kind of data set that you use to try out your different methods on, right? But it's one of these things that people just assume that everyone knows, and it's very rarely introduced formally in a class. So here it is. This is the MNIST data set. It's basically a data set of a bunch of handwritten digits, right? So a bunch of people are asked to write out 0, then 1, then 2, then 3, and you took images of these, right? So this, the data set we're going to be working with today, is each of these is an 8 by 8 image. So 8 pixels by 8 pixels, so a total of 64 pixels that correspond to, let's say, this 0, this 1, this 2, so on and so forth. And a classic classification problem might say, here's the image, tell me whether it's a 0 or a 1 or a 2 or whatever, right? So this is a way of testing out different classification algorithms, okay? So when I look at this particular setup, if I want to now find, say I wanted to find some kind of underlying lower dimensional structure, right? I want to project it onto some kind of lower dimensional thing. Well, I could say, let me try to find, some other vector that I can project onto. So if I think of my images, which are now 64 pixels, how do I represent 64 pixels as a vector, right? I have a length 64 vector. Right? And each entry in this vector is the value of that particular pixel. Okay? So I can think of this image as basically this vector of length 64. If I wanted to, let's say, choose some, 8-dimensional, let's say, underlying structure, some set of 8 vectors that represented this. Well, one example, one option that I could choose is I could choose the first 8 pixels, right? So if this was my image, the first 8 pixels are, let's say, this first row right here, right? And so here, this is representing kind of the unit vector corresponding to a 1 here and then 63 zeros, but it's just represented as a square, right? Does everyone see that here? This is kind of the second unit vector. So there is a 0, and then the 1, and then the remaining 0, so on and so forth. If I was to project this image along these 8 different dimensions, well, the projection of this in this direction, there's nothing, right? There's a white pixel there, basically. So I get nothing here. I project it along this direction. I get nothing here. Now I project it in the third direction. Oh, and there's some non-zero value here, so something's starting to show up, right? And you can, if you zoom in, you can see that they've actually computed exactly what the coefficients are. Then you can see, well, there's actually also something in the fourth pixel. Then in the 5th pixel, so now what they're showing here is kind of the sum of all of these components. Then you get something more in the 6th direction. And now, after you do 8, what you get, is this approximate image, right? Right here, which is the sum of the projections of this image along each of these 8-dimensional vectors, each of these 8 vectors. Everyone with me here? Is this a good approximation? It's not, right? Would you want to choose just the top 8 pixels to represent this? Probably not. The question is, how do you choose some vectors, right? There's a very large number of ways of choosing vectors in this case, right? So what we want to try and do is figure out what are the right vectors. And so here, what has been done is actually they've done principal components analysis on this data set. And they've projected the data along the first 2 components. So the x-axis is component 1, y-axis is component 2. Each of the colors corresponds to a cluster for a particular digit. So for example, the 0s are all here, the 1s are all these purple guys, the 2s are all these dark blue guys, the 3s are all these light blue guys, so on and so forth, right? And you can see that like things that are similar are clustering together, right? All of the 3s are close to each other when projected into the principal components dimensions. Does everyone see that? So the question is, how do you, if I was to just project into 2 random directions, I wouldn't get this. The question is, how do I find out where and how to project to be able to get this kind of nice underlying structure? And this can then help me build appropriate classifiers. Once I have a projection in a clean way, I can find the appropriate kinds of separating hyperplanes. Okay? So everyone see what the kind of thing that we're trying to do is? Okay. So this is kind of a cool looking example, but I want to now go into kind of a more principled example that helps us understand the underlying mathematics of what's going to be going on and what we're going to be doing. Before I go on, any questions about the previous Jupyter notebook? Yes? We are not quite trying to preserve the norm, but we'll get to that in a little bit. Hold that question. Other questions? Yes?
Are we trying to choose, in the principal component analysis, are we trying to choose which pixels have the most effect on our image, or are we like trying to just reduce our image?
It might not be a pixel, right? For example, a valid choice of vectors. For example, here I just chose something with a, just 1 here and zeros everywhere else. But I basically have an infinite number of choices here if I assume that every component here could take a real valued number, right? So a direction of projection is any 64-dimensional vector. Okay? So there's an infinite number of choices, assuming my entries could be real numbers. If my entries were constrained, let's say, to be binary, then how many would I have? I would have 2 choices, so 2 to the 64 choices, right? Still too many. Okay, so this next example will make things more clear, and then we're going to go through the mathematics of all of this, right? So I'm not doing any of the math right now. All of the math will become clear soon. Okay, so PCA on artificial data. So what I'm going to do is I'm basically going to generate a fake data set, and we're going to try and understand what the principal components of this are, right? So let's first say, let's generate some fake data. So let's generate some 2-dimensional data, right? I'm just basically using this to generate some clusters of data. So what I'm saying is, like, let's generate cluster 1, cluster 2, cluster 3, and cluster 4 with some mean and some standard deviation that's small. And if I plot them in my 2D space, these are kind of these 4 data sets, 4 clusters, right? Everyone see that there's 4 clusters that have shown up? And I've just created these, right? I've created these by choosing Gaussians with different means. Okay? So these are some clusters in 2-dimensional data. Great, right? If I just had this data, and if I just had these 2-dimensional vectors, I could plot them, I could see clusters, I could classify them very easily. But now, what if this 2-dimensional data was actually embedded into some kind of 25-dimensional space? How could I possibly uncover the underlying structure, right? So what do I mean by embedding into 25-dimensional space? To understand that, let's first look at what it means to embed in 3-dimensional space. So here what I've done is basically embedding in 3-dimensional space, I need to give each of these a z component, right? They have an x and a y component. Now I need to find a z component. If I gave them all the same z component, I could embed them in 3-dimensional space in a way that looks like this. Everyone see that? Is this the only way of embedding them in 3-dimensional space? No. Again, there's an infinite number of ways, right? I could embed them in 3-dimensional space in some other way. Basically, if I wanted to embed this 2x2 data into 3-dimensional space, I would multiply by any random 3x2 matrix, which would generate a 3-dimensional embedding of this underlying 2-dimensional data, right? Does everyone see that? So this is the embedding that, like, preserves the visual clustering. This other embedding, where I chose a different matrix, loses kind of that embedding, that visual embedding aspect, or the visual clustering aspect. So now let's try to do this in 25 dimensions. So, choose a random kind of 25-dimensional 25x2 matrix, and try to project each of these data points into that 25-dimensional space. So I generate this random matrix M, and then I multiply, okay? And now what do? Is I say, let me pick 2 random axes, right? Let me take my 25-dimensional data and project it down back into 2 dimensions in two random directions. I haven't chosen specific ones. It's not like choosing a particular pixel, but I just, any 2 directions that came out of hat. And this is the projection I get, right? So these clusters are still fairly visually preserved. If I could plot the 25-dimensional data for you, I would, but I can't. But now what happens if in my 25-dimensional space, I also add some noise? So now I took my vectors, and I added this noise here, okay? And I added quite a bit of noise. Like, I think my initial standard deviation was 1. Now I'm adding noise at standard deviation 5. So it's quite a bit of noise. Now when I project in 2 random directions, none of my original structure is preserved, right? This is what it looks like. So now the question is, can we, from this very noisy, it seems to have lost its structure because of this addition of noise. But can we somehow uncover the underlying structure, even though we have this kind of just cloud here? Turns out that we can. We're going to use principal components analysis, and under the hood of PCA is basically the singular value decomposition that gives us what the key things are. And so I'm going to compute these principal components using the SVD, and I'm going to project the data into my first two principal components. And I plot the result. And now I have recovered these 4 clusters, right? That structure that was there, by projecting into the right 2 directions, I see this structure. When I project it into random 2 directions, I do not see the underlying structure. Okay? So here is a more contrived example. It's not the MNIST data set, it's not real data. But by doing this on this kind of calculated example using Gaussians, we can see what we mean by trying to have the principal components and what the impact of these is. Okay? Any questions about this? Yes?
If you didn't know that this data came from a 2D, and you see the data in 25D, how would you know that the optimized way to separate them into 2D and not 3D?
Great question. So this is, so the question is, how do I know if I didn't, if I hadn't cooked up the example, how do I know to project into 2D, and why not project into 3 dimensions? So this honestly is done a little bit by trial and error in the real world. You will compute the top principal components, and you'll kind of project into the top few, your top 2 dimensions, 3 dimensions, 4 dimensions, to see what kind of underlying structure there is. The other thing that we will see is that every principal component will come with an associated weight, which will be the singular value associated with that particular vector. Okay? And the value of that singular, the value of that singular value will tell us how important that principal component is. And we're going to see that kind of in the rest of the lecture. Good question. Someone else. I'll prioritize people who haven't asked questions yet. Okay.
So if there wasn't any noise, were principal components here just be the x-axis and y-axis? So
If there wasn't any noise, would our principal components just be the x-axis and y-axis? It depends on your data set. Depends on how they're aligned. They could be, they could not be. Can't say that. Okay, any questions about any of these demos? Because once this is gone, like, the screen can't come back down. Yes?
The principal components in the MNIST example, those principal components, you could view them as like pictures, right, that get projected onto, like the 8x8 grids?
Yes, so if you wanted to, so actually here, if you were to compute the principal components in the MNIST example, this is what they look like, this top row. So these are the top 8 principal components, and when you project this image onto each of these are the projections that you get. When you add them up, this is what you get. Yep, so good question. Yes?
So the second row of images gives you like any input that you're trying to train on?
No, the second row of images is basically the dot product. It's the projection of this test image onto this one. So inner product of this with this gives you this. Inner product of this with this gives you this. Okay? So the coefficients of this are kind of the corresponding weights on each of the principal components for this particular image. Okay? Good. Okay, so that concludes that. Let's see if I can get this to go up. So what we're going to do is we're going to see how we can find, for given data points, x1, x2, all the way up to xn, we want to find the first principal component, so one dimension, or one direction, w, such that the projected vectors are as close as possible to original vectors. Right? And I want to have a unit vector, since it's just easiest to deal with things that are normalized. So what does this mean? Right? I want to project into a lower dimensional space, but I don't want to distort my data, right? I want to try and preserve the structure of the underlying data as much as possible. Does that make sense? So what I'm going to look at is I'm basically going to look at the error of my projection. Now remember, what is the projection of x1 onto w? W is a unit vector, so what can I write the projection as? It's basically xi for vector I, inner product w, times w, right? This is the magnitude, and this is the direction. So what I want to do is I want to minimize the error of my projection. And the error of my projection is xi minus the projection I'm just going to call this EI squared. So the error for point I, assuming that I project into direction w, is the difference between where my data point xi is and the projection. The norm squared of this is my error, okay? And so do I care about just minimizing the error on x1 or x2 or x3? No, I want to care about it across all of my data points, right? So I'm going to look at my average squared error, which is going to be just 1 over n, sum of all of these EI squared. Okay? So what I want to do is I want to minimize this projection error. That's my kind of desired goal in my principal component. Okay? Okay, so now when I look at this particular quantity, this guy, what can I say about it? Can you expand this out? This is basically just equal to xi transpose minus w xi transpose times this thing, right? The same thing. I'm not going to write it out again. Right? This is just the norm of a vector. So if this was vector v, this is just v transpose times v, right? What happens when you kind of use the distributive property and separate this out and get the simplification? Can you do it for a quick minute? You're going to get an xi transpose xi term, right? So that's going to give you an xi norm squared, right? Then you're going to get this times itself. So what is that going to give you? That's going to give you basically w inner product xi whole squared norm squared of w. And then you're going to get the cross terms, right? Sorry, what? Oh, sorry, this is not a transpose, yeah. Thank you. Everyone with me here? I feel like I've lost everyone doing multiplication. No, it's just really hot. Okay, let me write this out. W xi w. And then I get these cross terms, right? So I get xi times this, right? So this is a scalar. And so xi transpose w. So I get this inner product twice, right? So I get minus 2 WXI squared, right? This times this is the same, gives me the same as this times this, because I get, both cases I get WXI inner product. There's already this scaling, so I get this term, right? But now what is this quantity? This is just 1, so I can replace this with a 1. So this gives me xi squared minus w inner product xi whole squared. Because this and this are the same, and you get this. Yes? Could I review the? There should not be. But here, okay, what did I do here? I have this times this, right? So I have xi transpose times w inner product xi times w. This is a scalar. So, and this times this is also just this inner product. So I have w xi transpose w xi transpose, which just gives you the inner product squared. Okay? Yes? No? Okay, good. And so when I write this, I have every term is equal to this particular thing. I'm trying to minimize my error, right? So I can write this as a minimization problem. Trying to minimize over all w. I'm trying to find that w that minimizes this quantity, right? So when I now compute my average error and I add all of these up, what is my average error going to be? It's going to be 1 over n sum norm squared of xi minus 1 over n the sum of the inner products of w and xi squared. Everyone see this? Now, if I'm minimizing this thing, minimize over w. Which term do I not care about, given that I'm minimizing over w? What term doesn't matter, is not affected by w? This first term doesn't matter at all, right? I don't need to carry this around. So really what I'm trying to do is I'm trying to minimize minus of this sum, which means I'm trying to maximize the sum itself, right? So I can rewrite my problem as just the maximization of that quantity. So my problem is now maximize over w. The 1 over n doesn't matter either, so I'm just going to drop that part as well. Or we can keep it. It doesn't really matter either way. square of this inner product. Any questions up to here? Everyone with me? Yes? Okay. So now this thing is an inner product, right? And I'm taking this sum over all of these. So this is basically xi transpose times x1 transpose times w squared plus x2 transpose times w squared plus x3 transpose times w squared all the way. I can write this conveniently as 1 over n times my data matrix X times W whole squared. Right? Remember, my X is x1, x2, xn. Right? Each of these inner products is with these transposes here. So x1 dot w is that first row times w, second row times w, right? If I take that vector and I take the norm, I get exactly this sum. Does everyone see that? Now, is there another way I can write this that's like moving in the direction of stuff that we've been doing? It's a norm squared. So this is a vector, right? This is an n by 1 vector. So I can write this again as x w transpose times xw, which is equal to 1 over n w transpose x transpose x w. Right? Okay, so I did need x transpose x. What is this matrix? What did we do at the beginning of lecture today? We figured out the maximization of x transpose AX for a symmetric matrix X, right? What do we have here? The same thing, right? So what is going to be the direction that maximizes this quantity? The eigenvector corresponding to the largest eigenvalue of this guy, right? So first principal component is eigenvector corresponding to maximum eigenvalue of x transpose x. You should be happy. Okay? Yes, question? No, capital W is not a capital W. Capital W is just me struggling to write on a whiteboard very, very fast. Yes?
Why are you trying to maximize the error?
I am not trying to maximize the error. That's a good question. If you missed this, so I have the average error is this term minus this term, right? I'm trying to minimize this quantity. I decided to throw this term out because my choice of W simply does not affect this first term. And so I'm trying to minimize minus this. So minimizing minus this is the same as maximizing positive this. That's why I threw out the negative sign and wrote this as a maximization. Yes?
Is the 1 over n important because we have gotten rid of
The 1 over n doesn't matter. We could have gotten rid of it. It's just kind of standard because people define 1 over n times this matrix as the covariance matrix, and that's particularly useful, but it depends on which way you're doing it. If you're seeing a treatment of PCA that is probabilistic, sometimes people will use the covariance matrix much more. but it really doesn't matter. And now we're going to, like, this is using the symmetric matrix structure, but we're going to also see that this is basically most commonly done using the singular value decomposition. So we're going to connect now the eigenvectors of a symmetric matrix to the eigenvectors of, to the singular vectors of the matrix itself. So we're going to come to that in 1 minute. Question? Okay. So here, I'm going to pause here on PCA, and I want to now, so we could basically solve PCA by always computing x transpose x and computing its eigenvectors and doing that, right? But a way that principal components are often calculated is through computing the singular value decomposition, which is equivalent to this calculation in many ways. But the singular value decomposition has a lot of nice properties that are useful, and so it's useful to also just understand the SVD on its own terms. So let's get to that. And so what is the singular value decomposition for a particular vector, right? You've all done some homework on this, so you've been forced to kind of look this term up. And so the SVD of a particular matrix A, not necessarily symmetric, so A belongs to R m by n, is given as A equal to U sigma V transpose, okay? And dimensions here are kind of important. So A is m by n, and when we talk about the full SVD, we often talk about an m by mu, sigma, which is the same dimensions as A, m by n, and V transpose, which is n by n, okay? And so if A is, for example, a tall matrix, then its singular value decomposition will look something like this. I like drawing these pictures out because I think it really helps you visualize what the SVD is doing. So this is my A, this is my U. So if m is greater than n, this is m by n, this is m by m. This is my sigma matrix, but what does sigma look like? I want this to be kind of as much as possible like the spectral theorem, right? The spectral theorem was super useful. Am I going to be able to get a diagonal sigma here? No, it's not a square matrix, right? But what sigma turns out to be is it turns out to be approximately diagonal. And so I will have stuff here, this will be 0, and this will be a V transpose. And the entries along this diagonal are what are called the singular values of the particular matrix, okay? So this is the case for a tall matrix. If A was wide, then my U is the small one. Sigma is the same dimensions as A, and V is giant, V transpose rather. And my sigma here is again diagonal entries here and a 0 here. In general, the singular value decomposition can also be written in dyadic form. Where should I write this? What should I erase? This, can I erase this? I don't. Sigma 1, U1, V1 transpose plus sigma 2, U2, V2 transpose, sigma R, UR, VR transpose. So if I have R non-zero singular values, that means the rank of A is R, then I can write this as the following sum. And that's because basically every time I have a 0 here, the remaining vectors don't matter, right? And so I can write this out in this dyadic expansion, each of these terms is called a dyad. And this particular expansion is sometimes useful. So I do want to, how many people are comfortable with finding the singular value decomposition of a matrix? How many people are not remembering it very well? Okay. How many people feel confident about the geometric interpretation of the SVD? How many people would like a geometry of SVD review? Okay. It's like about equal. Okay. How about this? I will quickly go over the algorithm to compute the SVD, and we'll talk about geometry a little bit in the next class. So the singular value decomposition of a matrix is very connected to the eigenvectors of the corresponding symmetric matrices. So for example, let's say I have this A, which is m by n. I'm going to consider the symmetric matrix A transpose A, okay? And what do I know about this symmetric matrix A transpose A? Let's say it has the following eigenvalues, non-zero, lambda 1 greater than lambda 2, all the way greater than or equal to lambda r. These are strictly greater than 0, and lambda r plus 1 all the way to lambda n are all 0. Okay? And let's say the eigenvectors corresponding to it are v1, v2, all the way up to vn. These are the eigenvectors corresponding to these eigenvalues. Okay? So in this case, we know that A transpose A times v1, let's say, or vi, is equal to lambda I times vi, right? Because I'm saying vi is an eigenvector of A transpose A. Okay? So we already know that the null spaces of the matrix A and the matrix A transpose A are very connected, right? This is something that if it might be worth going and you know, looking up. It's worth doing a quick review. But in general, can I use these vectors to somehow generate the setup that I want, right? So I have this A transpose times A, and if I make these V's into a vector, into a matrix V, so if I make, this marker is dying. If I consider this matrix V, which is V1, V2, all the way up to Vn. This is a very useful matrix because what happens when I multiply A transpose A times this, right? Stuff starts going to 0. This AV is going to be ending up to be very useful for us. So why am I saying all of this? I'm trying to give you the intuition behind where the SVD algorithm comes from, or what is the method for finding the SVD. Right? It's not just a process that comes, you know. I don't have time to fully explain all of this to you, just given that, you know, this is only the review portion of the class, but I want you to try and see why I'm trying to do these things, right? So I know that A transpose A times Vi is equal to lambda I times Vi. And so now if I define sigma I to be equal to the square root of lambda I, and I define A times Vi to be equal to sigma I times some other vector ui. Right? I have this A A transpose A times V gives me some nice properties, right? This does nice things. This preserves null spaces in a sense. But I don't want this A here, right? I really want to care about this A times VI. So I'm going to try to pull that out. And this A times VI, I'm going to write as, I'm going to define UI as basically A times VI divided by this sigma I, as I've defined it, which is the square root of this lambda I. Okay? Turns out that UI and UJ are orthonormal. I'm not going to rush through this in the last 1 minute of proof that I have. I also feel like everyone is just so tired today. So how about we just end class a couple of minutes early? It's hot. Take a water break instead, and we'll pick up next class. I'll go through this again. Take an easy day.